All right, so we're going to move on to Module 6 for our final exam review on the focused questions from the study guide. Here it says, using a student's t-distribution for question 21, find the critical t-value for a 90% confidence interval when the sample size is 18. Okay, so basically, because we're working with a t-distribution, we want to make sure that we're using the correct chart, and that's going to be this critical values for students t-distribution chart here, okay, because we want to find the critical t-values. And if we remember from this chart, the values that are going to be the t-values are actually going to be inside of the chart, as opposed to it being the values on the outer rows and columns here, okay? So they want us to find a 90% confidence interval at a sample size of 18, okay? Now, if we recall from this table, this first row here, this first column here that defines all of our rows are based off of degrees of freedom. So we're going to need to calculate the degrees of freedom, which is everyone's favorite equation, n minus 1, where n is your sample size. The sample size was given to us as 18, so we're going to subtract 1 from it, and our degrees of freedom is going to be 17. That means that that's going to be our... We're going to go to the row with degrees of freedom of 17, and one of these values are going to be our answer. Now, which one? That's going to be based off of our 90% confidence interval. So if we go to C, which is denoted as like our level of confidence, we can find the value that's at 0.9 or 90% and use that column to help find our t-value. The intersection of these two values, of the degrees of freedom and our confidence interval, is going to be our critical t-value, which on our chart here is going to be defined as 1.740. Okay. So key things to remember here: make sure that you're using degrees of freedom when you're finding these critical values, and make sure that you are looking at the correct level of confidence based off of what the problem is giving you. Okay. Number 25, as the degrees of freedom increases, what happens to the student's t-distribution? Simply, this is that it starts to approach a standard normal distribution. This is a topic that we discussed in class a little bit too, but just to go over it a little bit here, the student's t-distribution is derived from the standard normal distribution, and it basically was a derivation that had less strict properties to it, so that it can be applied in scenarios where you have like a smaller sample size, or if you have something that's going to be basically a sample that's not as strictly defined by the normal distribution, with a lack of better words to say. So because of this, different assumptions can be made, and it could be applied to a lot more data sets than the standard normal distribution does too. But because it's derived from it, it's going to look very similar to it. So as we see here in the chart below, at a degree of freedom of 3, we see that in this black curve that it does resemble like a very widened normal distribution, with purple being the normal distribution. And as we increase our degrees of freedom, as we see in the blue chart here, we start to get closer and closer to mimicking the standard normal distribution, okay? So basically at the end of the day, the reason as to why it starts to approach a standard normal distribution is that the t-distribution is derived from it, okay? And we just want to know that it does approach this standard normal distribution as we have more and more, as we have a larger sample size, to say with a lack of better words. Because if we recall from the degrees of freedom equation, it's based off of n minus 1. So we could sort of think about degrees of freedom as sample size. And that sort of makes sense as our data, or as our sample size increases, we start to include more and more people in our population. So if that population is assumed to have a normal distribution from the beginning, if we add more and more people into it, we're starting to mimic the population more and more. So we're starting to get towards that natural distribution of the population, which here would be the standard normal because the t-distribution is derived from it, okay? Number 26, as the degrees of freedom or sample size increases, what happens to my critical t values? So here we have an inverse relationship. So as the sample size increases, the critical t value decreases, and as the sample size decreases, the critical t value increases. And we can see that simply from our chart here. So if we think again, degrees of freedom is equal to n minus 1, so very related to our sample size. We can think about an increase in degrees of freedom as an increase in sample size. So as we're going, let's choose like any of these columns, it doesn't matter. Let's choose this first column just for simplicity. As we go from like 1 to 10, we see that that critical t value is decreasing. And if we go even more to 19, that value has decreased even more. So here it's just being able to interpret the chart and seeing what that trend is for the critical t values, okay? So, and vice versa, if we look at the values from 19 to 10, that value is increasing as we decrease our sample size, and from 10 to 1, the t value is increasing as we decrease our sample size. Okay. Number 27, what are the assumptions required to use the student's t-distribution when performing a hypothesis test or confidence interval about the mean? Okay, so a couple things that you'll need to know for the student's t-distribution assumptions is that you need to have a sample standard deviation. This one's easy to remember because when we do anything with the t-distribution, you're going to be using the standard deviation, sample standard deviation inside of your equations there. Here, you want to make sure that there's no outliers in your data set. If you do, you want to like eliminate them or figure out an adjustment for those. And the data must come from an approximately normal distribution. This sort of comes from the topic that we talked about earlier, where the student's t-distribution is derived from the normal distribution. So we sort of need to approximate that the nature of that data set to be similar to the nature of the t-distribution, which is that normal distribution there. So we have to make sure that they're basically alike in its essence. Also, the big part here to remember is that the population standard deviation is not an assumption required for the student's t-distribution. And it's because when we're using the student's t-distribution, we're basing it off of like our sample metrics basically. And if we had the population standard deviation, we can use more powerful metrics such as the z-score and so on. So if the population standard deviation is known, then the student's t-distribution would be more obsolete because there are more powerful tests that you can use. Okay, so you only need to know sample. You don't need to know population. Okay. Let's see. Number 28. What are the main indicators on whether we should use a z or t distribution when running a hypothesis test for the means? I mean, obviously, we need to know that we're running a hypothesis test. As we talked about in the previous one, we want to assume that the data comes from our normal distribution. But I think the biggest indicator here is that there's no information about the population standard deviation given. Because that sort of gives us, that's that turning point, basically. When we have the population standard deviation information given to us, go ahead and use the z-score. It's included in our equation, where z is equivalent to x minus mu all over the population standard deviation, right? So when you have the population standard deviation, you can use a z-score easily. And then with that t-distribution, it's going to look a little different because we're working with that sample standard deviation divided by the square root of n. So again, that's going to look something like this. Right? Just making sure. Yep. And here, you're going to be using that sample standard deviation. So putting the two together, if you have population standard deviation, you're going to want to use the z-score. If you don't, you're going to want to use the t-score. Okay. If we run a hypothesis test for the mean using the t-distribution, what would the critical t-value be used for running the following test sample size and alpha value? If it's left-tailed with an n with a sample size of 30 and an alpha of 0.05. Okay. So here, it's reading the chart as it is. So given that we're working with a left-tailed test, this is going to be one-tailed. Oh. So we're going to be using this top row instead of the middle row in some part during this, during finding all of these values, or finding that critical t-value specifically. Okay. A sample size of 30 means that our degrees of freedom is going to be 29 because we take 30 and subtract 1 from it. Okay. Which means that we're going to be working with this row. And an alpha of 0.05 is going to give us the column that we're working with, basically. So if we look at the one-tailed test, we want to find 0.05, which is in this column for the one-tailed row. And then from there, you want to connect that row and that column together to get your critical t-value of 1.699. Okay. So the big things here is to make sure that you're using the correct area, one-tailed versus two-tailed. Okay. And because of that, you want to make sure that you're using the right row, because if we ended up using the two-tailed, we'd be one column over, and then we would get the wrong answer. Okay. Also make sure that you're calculating degrees of freedom, just like in that previous, in a couple problems before, we talked about making sure that you're using degrees of freedom for this table. And you should be good here. Okay. All right, question 30. Cinnabon claims that their cinnamon rolls weigh 7 ounces on average. We believe that the cinnamon rolls are larger than they claim to be. If we want to test this claim, what would our alternative hypothesis be? Okay, so if we remember for alternative hypotheses, these are going to be symbols that do not have like an equality to them. So it's going to be less than, greater than, or not equal to. Okay, so we're going to want to use one of those three symbols for your alternative. And similarly for your null hypothesis, you're going to have some kind of equality to them, less than or equal to, greater than or equal to, or simply equal to. Okay. The test likes to use just equal to for the null hypothesis, and in class I liked using the distinctions between greater than and less than because it gave like that whole picture. But whatever suits your fancy here, especially because here we're talking about alternative hypothesis anyways. Here they're saying on average, so we know that we're going to be using a mean symbol. And the initial claim is that they weigh 7 ounces on average. So we're going to say that, just to follow what the test format is going to be, that we're going to have it equal to 7. Okay. The claim that we're testing is that it's going to be larger than they claim to be, which, I mean, I wouldn't complain about. That means you're getting more cinnamon roll than you're advertised for. But that's going to give you, since it's going to be larger than, we're going to be working with a greater than symbol. And you're always going to be using that population mean there. So because of this, we're going to have the population mean is greater than 7 as our alternative hypothesis. And that concludes our model.